Okay, we are live. So, 10.1, sequences. The number one thing to understand when we are looking at the difference between a sequence and a series is going to be the fact that a sequence is simply like an ordered collection of numbers. So it's like a list of numbers, 1, 1/2, 1/4, 1/8, etc. So obviously there is some sort of a pattern happening, but it is the list, and we can refer to any one of those terms as just that, as a term, an nth term of the sequence, right? So that would be the general term, and this is some of that background knowledge that I think that we're all, relatively comfortable with. Okay. Sometimes sequences can be defined recursively. So this is an example that I'm not going to go through with you because I think this is background knowledge that we would have. So if the example given is to compute A2, A3, and A4 for the sequence defined recursively, where A1 is 1 and then AN, the general term, is 1/2 parentheses A sub n minus 1 plus 2 over A sub n minus 1. So an example like this, of course, we just go through, we are given A1. So with A1, I'm able to find A2 by plugging into the recursive definition and so forth. And then I could find A3, and then I could find A4. And in each case, I do have to simplify and come up with the fraction all the way at the end there. So I'll pause and let you copy down what you need to copy down. What they're really showing here, right? The big topic that we're going to be exploring over these sections, so this class period, is the idea of convergence and divergence, and that will continue through. So in this example, if I were to take the calculator and find the decimal of these fractions, they do approach this 1.41, which means that this is converging to a value. So our sequences and series, they can either converge to a value, a finite number, or they can diverge to infinity, or diverge where they sometimes bounce back and forth between values. Okay, it doesn't have to be unbounded. So a suggestion as we move through this chapter, and really this will start to come up into 10.2, is start creating, I guess, like a formula sheet or test sheet. There's going to be different types of tests for divergence and convergence that you want to start writing down. It's not that this is a sheet that you would be able to use on the AP or assessment, but as always, when you're learning new rules, the more you write them, the more you look at them, the better you're going to be at using them. So the challenge in this chapter is the problems might start to really resemble one another, and understanding, well, which test do I apply here so that I can come up with my answer. Okay. So the second, go for it.
So it's a little off topic, but also on topic.
Okay.
So for our AP physics class, we were told that the College Board is cutting certain units out. And so do you know if like certain units are going to be cut out for BC?
I haven't heard that for BC.
I think it's only for physics. Are you in AP Physics 1?
Only physics, yeah.
Only physics.
Only AP Physics 1 as far as I know.
Like if we could chop off chapter 10, we'd all be good. Okay. No, nothing's being chopped
Got
off.
a formula sheet, that would be good.
It would be good, right? If we could be done, it'd be amazing. I would definitely jump on board with that. But sorry.
All right.
Last year they did that to calc. This year, no. But the good news is we will finish our content on time. We're fine. All right.
What does the bottom of the board say? Like at the very bottom?
So I have some decimals, so the fractions approximate to 1.4167 and 1.414216.
Okay.
The textbook has a lot of this stuff in the side, like tables and different things that you can pull from. So I pulled some key information. Otherwise, it is definitely helpful to follow these examples along with the textbook as well.
Mhm.
And then I just scribbled the word convergence.
Can you zoom in on the work you did for A4? It's a little blurry on my side.
Sorry. This isn't ideal. How is that better?
Yeah.
Okay. So I won't change the page quite yet, but example 2, I'll show the definition, but we're not going to go through example 2. It's the proof of this limit of a sequence, and it's not something that we'll need to use as it's shown in example 2. I'll show a different example, and that is more than we need. So I'm actually going to flip all the way to theorem 1 and example 3, and then just do a quick flashback to example 2 and the definition of the limit. And then I think it makes more sense. So let me erase this. So we have theorem 1 saying the sequence defined by a function. So if the limit as x approaches infinity of f of x exists, then the sequence where a sub n is equal to f of n converges to that same limit. And so if we can take the limit of a function, then we can take the limit of that sequence as well. And that, again, a sub n is that nth term of the sequence, and they would be equivalent. Those limits would be the same. So find the limit of this sequence. So they define it for us with the different terms, with the different values. We have to come up with the a sub n definition of it, okay, based on what's given. So we would say, well, the pattern that we're seeing, right, is n squared minus 2 over n squared, right? This can actually be simplified, even though it's not written in this fashion in the sequence, but we could divide each term so that we have a 1 minus 2 over n squared. Either way, we could actually explore the limit from, and I'll talk about that in a second. So we can also say if this is equal to a sub n, well, then we can call this also f of x and just replace the n's with x's. It's the same idea. Rather than a sequence with respect to n, it is a function with respect to x. And then therefore, this theorem is saying that the limit as n approaches infinity of a sub n is equivalent to the limit as x approaches infinity of f of x. And more specifically, in this example, the limit as x approaches infinity of 1 minus 2 over x squared. So we're going to be using quite often in these examples, and I'm going to have to speed it up so I don't run out of time, but quite often in these examples, we're looking at the degrees, right? We've talked about limits at infinity, just comparing the degrees of the top and the bottom and deciding where does it go. Some of the videos, the Khan Academy videos were good, and he takes it further. You don't actually have to go and divide each term by the largest degree. We can see that obviously 1's 1, and then 2 over an x squared would zero out. So this limit would equal 1. So when I was saying that, yes, the textbook offers and suggests that we simplify to here, you don't really have to, because then just taking a look at this format of it, if I think about the degrees, well, now I have the same, and the ratio of those coefficients is 1. So I would still arrive at the same answer. So I'm looking at it for like the 3rd time through now, or 4th time, and that's sticking out at me. So sometimes we don't have to simplify things all the way like that. All right, so then if I just take you back to this page, it is saying the same thing in certainly a more confusing way. Certainly more. And it's, I was relieved. I did ask Mr. Reyes, so we're good. This is not necessary. It is simply saying the same thing as the other theorem just said, that the limit of a sequence is equal to the limit of the function, as long as, of course, they are the same thing. So then the limit as n approaches infinity of a sub n equals L, or that's implying that a sub n is approaching L, right? Then it gets more complicated down here because they just introduced extra letters or symbols in order to fully define this. But again, theorem 1 summarizes what this is saying. Limit of the function is the same as the limit of the sequence. One thing that is important to note, that if the limit doesn't exist, we would then make the conclusion that it diverges, right? If we can't take the limit of a function, then it does diverge. Go ahead, Simon.
I was wondering, you said that it generally summarizes the previous function, but do we need to write it down in our notes for future use?
No, you do not. If you're curious for the proof of it, essentially, you can follow along in the textbook, but no, you don't need it. You don't have to put it in your notes. You could cross it off if you would like to, and star theorem number 1. That would be the same thing.
Thank you.
You're welcome. Okay. So we did that one. Okay, so I'm going to erase this. And let's take a look at example 4 together. So calculate the limit as n approaches infinity of n plus L of ln of n over n squared. So this really, it's in 10.1, but this is a 4.5 question. This is actually going to turn into L'Hopital's rule. So they're calling that, that's a sequence, n plus ln, n over n squared is a sequence. But if we want to take a look at the limit as n approaches infinity, all of these rules that we've worked on can still be applied in the same exact way. We're looking to find the limit as a function to see, is this diverging or is this converging? That's the big picture that we're looking for here. So writing it as a function would be the first step in using theorem 1. So this is equivalent to saying limit as x approaches infinity of x plus ln x over x squared. Okay. Then if I try to just kind of evaluate it as is, I would have some form of an infinity over an infinity, right? I might right off the bat just say, well, the degree's larger in the bottom is going to grow faster. I might go with that, but I might say, I'm not positive. There's an ln in there. I don't have true just exponent comparing to exponent. It's not just irrational with polynomials. So I can explore this because it has that form of infinity over infinity. So then this would then be equivalent to, if I derived each top and bottom independent, I would get 1 plus 1 over x over 2x. And now if I take a look at this and kind of plug in my infinity, right, I have 1 plus 1 over infinity, or 0 over infinity. So number over infinity goes to 0. Okay, so this series is, or this sequence, I'm sorry, a sub n, this term is going to converge to 0. The list of values eventually zero out. All right, this next example, it is certainly helpful to have the textbook in front of you. I'm not even going to erase because it without all of the content, there's graphs and there's tables of information. So there's context to it here, but I didn't grab everything. It's talking about Balmer wavelengths. So a quick summary of what that is. It's the ionization energy of the hydrogen atom. So if you're interested in that kind of stuff, it might make sense to take a look at the graphs that they provide. So the series, the B sub n term for the sequence, I'm sorry, is given as 364 and a half n squared divided by n squared minus 4, where n is greater than or equal to 3. That's an important note right there, that sequences don't have to begin at 0 or 1. They could begin at any n value and continue from there. So all that we're expected to do at this point, right, is just calculate the limit as n grows to infinity. So same step as last time, I converted it to a function, and then I just compared the ratio of the coefficients. The x squareds are the same degrees, so that coefficient of 364.5 is where these Balmer wavelengths are going to converge to. Okay. Okay. Geometric series.
Wait, what does it say
Sorry.
in the previous slide on the top right corner?
Oh, that's just a quick summary of what Balmer wavelengths are. It's ionization energy of the hydrogen atom is what I summarized. It's in the textbook, more specific than that. Okay, so I'm going to erase this so we can analyze this a little bit more closely. Okay, so a geometric sequence, right? That's something that I think you've seen over the years, and I don't know how deep into it you went in pre-calc last year. But obviously we need that common ratio with all geometric series and sequences, and sometimes it's going to be given and sometimes we're going to have to find it. But ultimately this question is just in general, we want to prove that the limit of CR to the n power which is a geometric sequence with r greater than or equal to 0, they're suggesting, goes to either 0, c, or infinity, and we want to prove that. Okay, and the three piecewise domain are from 0 to 1, at 1, and then larger than 1. So the first thing, if we call f of r, our function, is equal to cr to the x, where r is between 0 and 1. We're thinking of this, right? So r is a fraction. So we're thinking as n approaches infinity, cr to the n, or if you wrote it as x approaches infinity, which I will here, right? As x goes to infinity, and if r is a fraction, something less than 1, then really the denominator is growing faster than the numerator, right? So we could say that this is equivalent. I can pull that constant out. It's not really necessary for my limit. And I'm just looking at this r to the x. And again, if r is a fraction less than 1, then this zeroes out. So it converges to 0. If r equals 1, then it really doesn't matter in terms of how quickly x is growing, because the limit as x approaches infinity of f of x really just becomes, we'll take that c out of there, r to the x, but r is just 1. So no matter what the exponent is, it's 1, and then we times it by c. So the constant is what's relevant there. So it still converges to that constant. And then the last scenario is if r is greater than 1. So now our base is 2, 10, whatever. So the limit as x approaches infinity of f of x, we can pull that c out, as always. And we would have r to the x, and that is going to grow unbounded to infinity. So that one diverges. So that's just kind of a proof in general based on whether our r is fractional, less than 1, actually 1, or greater than 1. Okay. The next slide, I apologize. I grabbed this and added it, but I didn't update it on Canvas. These are in the textbook. So I'm going to show them. They're the obvious limit laws that we've seen in the past, but they're now applied to sequences. So I won't stay here forever for you to copy them. They are in the textbook. You don't have to copy them for credit for your notes, but acknowledging them is important. So let me zoom in so we can talk about it a little bit. Right, as long as these limits exist, right, L and M, then if we're adding those two together, we can break them apart, we can expand them, we can add their limits. Similarly, if they're attached with multiplication, we can break them apart, right? So all of these limit properties we saw back in chapter 2, they're similar to the properties of the derivative that we saw in chapter 3, etc. As long as they exist, right? And here, as long as it's not 0, then we can do the division of it. So that's all good. Same idea with this constant. I was just using that property. I can take a coefficient out and put it out in front. And then the end result would be c times the limit for any constant c. And then our friend, the squeeze theorem, comes back. Remember, we use that a little bit, very special cases. We use the absolute value with it a lot. Same idea here. If we can prove the limits on the outer sides of the inequality, the upper and lower bounds, then that obviously squeezes and proves the limit for that inside sequence or function for that matter. Okay, so if limit of the b and the c equals some L, then the limit of the a also equals that L. Written exactly the same way, but we're taking this idea that we can look at a sequence just like we look at a function. And then all of these limit rules apply. okay? With the mindset of finding and proving convergence versus divergence. Right, so this is a pretty basic squeeze theorem. I'm going to leave the work up and just talk through it real quick. Show that if, right, this is a given, if the limit as n approaches infinity of the absolute value of a sub n is equal to 0, then the limit as n approaches infinity of a sub n is also equal to 0. So we can take this idea that we're given one of them, right? We can just look at the flip side of it, the negative of it, and then put a sub n in the middle. If we know this is true, and by limit laws, this negative is just a coefficient, I can pull it out in front. I know that the limit of this is already 0. So -0, it's still just 0. So I've just proven that the left and the right side of the inequalities both have limits of 0, and therefore the middle must also, right? And obviously anything coming out of an absolute value that actually is a value of 0, doesn't matter if it's a positive, negative, or the actual thing, 0 is still 0. Okay, so that's a very basic form using the squeeze theorem there. Okay, this next one, I'm going to clear out. Example 8 is geometric sequence, very similar to what we were just doing, but now the R value is negative. It's less than 0. So backtracking to that piecewise where we were proving whether the geometric converges or diverges based on R, we're gonna do the same thing, but on the negative side of it. Okay, so geometric sequences with R being less than 0. So we have a negative base. Prove this for C not being 0. So we want to show that the limit as n approaches infinity of CR to the n power is equal to 0 if R is between 0 and -1. So that's going to be really similar, right? It won't matter so much because it's a fraction, it's flipping it. Bottom line, that denominator is growing faster than the numerator. So at infinity, it will 0 out. So that work looks really similar. So we can call our function is CR to the x power. Right, we're looking at R's that are less than 0 and greater than -1. So therefore, these are all fractions. So the other way we can think about it is that the absolute value of R is then greater than 0 and less than 1. And we already proved this one to be true, right? We've already shown how the limit here, the positive of it was 0, and therefore it's going to give us the same exact result without the absolute value, because 0 is still just 0, right? Using the same logic as we did before, or just kind of skipping steps, because absolute value of 0 doesn't change anything. Now, the other one is where we want to look a little bit closer, where it diverges. So most commonly so far, something that was diverging was going on unbounded to infinity. Here's an example where it's not going to go on unbounded necessarily. If we have, using the same function, but R is now less than or equal to -1. The main thing that we need to acknowledge here is that if R is -1 and we keep raising it to different powers, n is growing to infinity, it's going to alternate. Positive, negative, positive, negative, positive, negative. Going to alternate signs. And therefore, it's not going to converge to any set number. But at the same time, it's not going to converge to the same infinity or not. So the absolute value of CR to the n, we can talk about the fact that, yeah, that grows very large. And if we do the absolute value, it grows large in whatever, the positive direction. And positive infinity. But technically, we don't have an absolute value here, but using absolute value just allows us to acknowledge that it's not converging to a set number. It is diverging. And oftentimes that's all you need for your answer. Just point blank, it diverges, done. I don't really need to know where it's headed, positive or negative infinity, but it's not headed to one common value. Okay. And the reason is because of that negative being raised to a power, it is alternating.
Wait, for the -1 is less than r is less than 0, wouldn't that also alternate?
Yes, it does technically, and at small values, when they're fractions, you're correct, Sophia. But ultimately, that denominator is what's growing, either positive or negative, very, very large. And that numerator is still just a number. So it's still zeroing out. So you might have oscillation or bouncing back and forth, positive and negative, but it is closing in on 0 because it's a fraction.
Okay.
Right? Because if I had, whether r was like, let's just say that r is -1/2, right? So if I have -1/2 to the n, as n increases, right? Yeah, the even ones are going to go positive, but they're going to go positive and approach 0. The odd ones are going to remain negative, but they're still going to approach 0. So you'll have some values from below approaching it and some values from above, but they're all going to 0. Whereas I don't exactly have a graph to show you for the other one, but I'm assuming that as we continue to go across as n or x approaches infinity, we're going very large negative and we're going very large positive. So they're totally going in opposite directions for r being less than -1. We're doing on time. I have until 11:50, so 25 minutes. Okay, pretty good. Okay, let me erase this and talk through this one.
Excuse me, I lost a bit of track. Are we in 10.2 right now, or are we still in 10.1?
10.1 is literally the longest section of this textbook. As I was going through, there's 12 examples. So we are
Yeah.
still in 10.1, Simon.
Yeah.
12.2 is quicker. So that's why I know that we're going to be okay with time. And I have just a few more examples that we'll go through. So this one, proving that the limit as n approaches infinity of r to the n over n factorial equals 0 for all r's, right? So we're going to, for the sake of this proof, we're going to assume that r is positive. And we're going to call m a positive integer, capital M. And we're just introducing these values to have some basis for our proof here. Okay. And we're going to say that R is between M and M plus 1. So it's some value between there. And we're going to prove this for values where N is greater than M. Okay, so these are all essentially givens. All right, so then therefore this sequence is equivalent to, if we just kind of list out the terms, it would be an R over a 1 times an R over a 2, dot, 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 right? Continuing until R over an M. So this we could call, that portion of it, we could call some constant C. And we can claim that this value is greater than or equal to 1. Then the rest of it comes from R over M plus 1. Right, we can claim that because of the inequality that we have here. Right, my R is bigger than my M. So all of these terms we're good on, and this is going to be some constant larger than 1. But then after that, right, now when R is above M plus 1 and R is smaller, now we no longer have values larger than 1. And this will continue until R over N, until we've exhausted all of them. Right, so this is each of them is less than 1. So then this is going to be less than or equal to, right? We can put a C here to summarize this constant C. And an R over N. Right, this constant C leading all the way up to here is going to be larger than these values. So, so this is going to be larger than that whole thing, right? Because these are continuing to make it smaller and smaller and smaller. Okay, so if we chunk that out, then that statement is true. So based on this, if we use kind of the squeeze theorem logic and we come up with this inequality, putting our sequence in the middle, and the value that we just proved would be on the right. Right, CR over N, that limit as N approaches infinity would be 0, right? The denominator would grow to infinity, the constant up top would, so it would cause a 0. We already have a 0 over here, because we're saying we're starting with some positive value, so we're squeezing it between zeros, which then proves with the squeeze theorem that this must be 0 by squeeze theorem. Let me know if you need me to zoom in on anything, people at home.
What did you do with the, why did you put the first chunk as constant C?
Okay, because it is going to be some C value and it is going to be larger than 1. So that's significant because after this chunk, once we transition from M to N plus 1 based on that inequality, our fractions turn from larger than 1 values to smaller than 1 values. So then in the whole scheme of things, this inequality, that ends up being larger because these in-betweens are making the total amount smaller and smaller and smaller. So if I chunk those out and I say some constant that's bigger than 1 times the very last term, well, that will be bigger than all of them together because I'm removing the ones that are making it smaller. It's kind of like you work up bigger, 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 and then all of these are making it smaller, smaller, smaller until you get to your last one. So if I can take those and remove those and just leave my last one, the expression, keeping the R and the N in there, then I know that that together is larger. So even if I said, like if I were to stop this right here, right, this is some constant larger than 1 times only a single term that is smaller than 1. So I can make those types of claims because of the fact that R falls between M and M plus 1. Okay. The next one, example 10, I actually find to be pretty straightforward. So I'm just going to explain it and not erase my work for the sake of time. So theorem 4, another theorem from limits. We've used these before. especially when we use L'Hopital's rule and we needed to apply the E and the ln. That was one example of when you can basically extract operations, quote unquote, from limits and apply the operations at the end. So this is saying that whatever the function is on that a sub n, we can pull that function out and then directly find the limit of just a sub n, and then the answer of it can then be plugged into the function. It would all be equivalent, is what theorem 4 is saying. So in other words, they explain it as bring a limit inside a continuous function. Okay, so our sequence is a sub n equaling 3n over n plus 1, and then we're going to apply it to the functions e to the x, which is continuous, and x squared. Okay. So the first line of work here is we are proving the limit of a sub n, that it equals some value, that it does converge. Because I have to get an L value in order to plug that L value into my function. So the limit of a sub n is n approaches infinity. Well, I have this rational function where my degrees are the same, top and bottom. So then I just take the 3. So then I can take that 3, and I'll just show example A for a second. You know, and I can write f of a sub n would be e to the a sub n power, or e to the 3n over n plus 1 power. The limit of this, well, in order to get to the root of what I need to get to, the same idea here, I can remove, these are in between that you don't have to put. I can remove the e outside of the limit. Like this. Then I already know the limit of this. It's 3. So then my final answer is just e cubed is all that it's saying. You don't have to show all these steps. I'm just showing all of them because this is the first time we're doing it. The second one is the same idea. G of a sub n would be 3n over n plus 1 squared, which is the limit of the a sub n squared. Extract the squared, take just the limit of the 3n over n plus 1. We showed it was 3, so then my answer is just 3 squared or 9. Let me know where you need me to zoom in.
Could you zoom in on the steps for A again?
I can't get them all at once.
Excuse me, should I be fine if I just got the theorem down? Or should I?
Yeah,
have
you're fine, Simon. I mean, in terms of credit for notes, right? Put your theorems down, people. Quick summary of an example or so. There's a lot of examples here. You don't need them all. You don't. Thanks for asking though. So big picture here, find that limit, and then just take the answer of it and plug it into the function. That's all I'm doing at the end. When you get to the final answer, it's e cubed. The other answer, it's 3 squared. It's 9. Done. But acknowledging that the theorem holds true here. Continuous function, limit exists. Okay. Okay, lots of words again here. Don't feel like you need to copy these down. They're in the filled out version. And if you don't have the filled out version, you don't have to write them all down to submit notes. So bounded sequences, you can be bounded from above. They'll call that a capital M. Kind of like a horizontal asymptote is the way I visualize it. You can be bounded from below, a lowercase m, a lower bound. The sequence a sub n is called bounded if it is bounded from above and below. The sequence that is not bounded is called unbounded. Go figure. Theorem 5, convergent sequences are bounded. If a sub n converges, then a sub n is bounded. If it ends up going to a value, it's bounded. Bounded monotonic sequences converge. So if a sub n is increasing and it has an upper bound, then that means that that it converges and that the limit has to be less than or equal to that upper bound. Right? It kind of like has a ceiling up there. It's increasing, but it's going to stop eventually. So it has to converge and have that limit.
It's like a horizontal asymptote, right?
Right. Same idea. Yes. Yes. But if it were decreasing and had an upper bound, those aren't consistent statements. That wouldn't help us.
Right.
If it's decreasing and has a lower bound, then it has like a floor, right? It has that horizontal boundary down below. It's converging. It might not converge at that lower bound. You don't necessarily have the information to prove that all the time, but eventually it'll converge at most the upper or the lower bound. So this example, it's in the text. We're running a little short and I want to make sure I get to the next section. Essentially what it's proving, verifying, I know it's so small for you to see it, verifying that a sub n equals square root of n plus 1 minus square root of n is decreasing and bounded below. So the decreasing and the increasing thing, that's like a first derivative test. If I derive it, then I know I have these square roots, these negative square roots, they drop down. This is larger than this. And therefore the whole thing, because it's subtraction, is negative. So if my derivative is negative, I am decreasing, is what I've just proven. They have a table of values, obviously that came from a calculator to show that there was a bound. All right, so that's something that you can pull from the side of this example 11. So the table was showing that a sub 1, a sub 8, etc., was getting closer to like 0.4 and then 0.17, etc. So all that they're showing there, it's decreasing. It does have a lower bound. It's bounding out at 0, right? And then therefore, because it's decreasing, the table's decreasing and is approaching 0. Little n is 0, therefore it converges. Therefore, my limit just has to be greater than or equal to 0. That's all that it's proving. I can't say it is 0, but it's greater than or equal to 0. Okay.
Wait, that says greater or equal to?
It does. It does. I'm sorry. It's very sloppy. It was late last
Can I
night.
just see the top right corner?
Top
What
right
you-
corner, I just threw down a couple table 3 values that they had written. A1 was approximately 0.4142 and A8 was approximately 0.1716. They had everything else and they're just coming from the original function. So this could be a calculator question where you could pull up your table of values. You could see where it's headed. You can prove that it has a derivative that is decreasing or a derivative that is negative and therefore decreasing. Mr. Reyes said, don't worry about it. If you want to look at it, it's in the text, but too much unnecessary stuff. Okay. There's a summary, which is always nice when they have nice summaries. Sometimes they're good, sometimes they're not so great. I grabbed it here, it's here. But I want to move into 10.2. We've got about 10 minutes. Some of the examples are easy, some are not. But I'm feeling pressure to get this in. So 10.2 is summing an infinite series, right? So the difference between the two is one of the examples that we're looking at, the sequence versus the series here. And a truly infinite series, right? That the word infinite implies that it goes on and on and on forever. But we can get what's called a partial sum, right? And oftentimes, not always, but that's what we're still proving, these partial sums converge to values. And then that would be enough information to say, well, this infinite series converges to this value. I don't care how long I go on for, this is what I'm going to get. So the example they give is actually sine of 1, part of the Taylor series, which we're going to cover in 10.7. So anyway, sine of 1 is actually calculated by doing the 1 minus 3 factorial plus 1 over 5 factorial minus, etc. And if we were to go through that and come up with the decimal result for each of the partial sums, so the first one, and then the second one is the first 2 terms put together, the third one is the first 3 terms put together, etc., we are seeing that it comes to this 0.8414, etc. And if I went to the calculator for sine 1, I would get the same thing, almost, right? It's only off by 10 to the negative 9. So this is just an example in the beginning, just representing what a partial sum means. If it does converge, it's enough to say that this is your value. Okay, so a couple of examples that I want to get to, and then it's fine. We'll call it a day, and I'll continue with this on Thursday, and that's fine, okay? Convergence of an infinite series. So an infinite series, there's a lot of places that, just a sidebar right now, there's a lot of places where words are like the last letter of a word is chopped off. I don't know why it does that. It's in the real book in places too. So anyways, an infinite series n equals k to infinity, a sub n converges to the sum s if its partial sums converge to s. And therefore, we would say that the limit as n approaches infinity of s sub n equals s. And in this case, we can also write s is equal to the summation from k to infinity of a sub n. If the limit does not exist, we would say that the infinite series diverges. If the limit is infinity, we say that the infinite series diverges to infinity. So continuing with the idea of convergence and divergence, but now we are looking at an infinite series and partial sums. So collectively everything together versus a single term, okay? Okay, so we'll call this the last problem I do, and I want to do this from start to finish. So the telescoping series, this is a good one, and it can be a little bit complicated, but it brings up one of the first methods that you're going to have to know how to use. And it gives us the identity here, but the problems might not always give that to you. So we are actually using something from our last module, our last chapter. We're using partial fraction decomposition. Right, we're taking one fraction and we're breaking it apart into two fractions, the A and the B idea. Okay. In order to prove this. So the question is, investigate numerically. The S is equal to the summation from 1 to infinity of 1 over n times n plus 1. And then we're going to compute the sum using this identity. Okay. So to investigate, I'm just going to start with S1. And using that identity, I would have 1 over 1 plus, or I'm sorry, minus in this case, minus 1 over 2, or 1 plus 1. And that, of course, equals a half. 1 minus a half is still a half. And then S2, if I continued to investigate, I would have 1 over 2, which was the answer I just got, plus, so there's two ways, right? I can look at it this way or this way. So my second term, if I was just finding it by myself, independent of anything else, I would use the first one. I would say, all right, then it's just 1 over 2 times 3, or 6. And then I would add them together to get my answer. But if I'm truly investigating, take a look at this. So if I use the right-hand side and S1, right, because S2 is S1 plus S2. So S1 is this 1 over 1 minus 1 over 2, plus S2, using the second method, would be 1 over 2 plus, I'm sorry, minus, I keep doing that, minus 1 over 3. And we can see that, take a look here, the halves cancel out. So I'm left with 1 minus 1 over 3, which of course would be the same answer I would get if I used that first approach. S of 3, so I could do it the first way, 1/2 plus 1/6 plus 1/12, because I would do 1 over 3 times 4, or 1 over 1 minus 1 over 2 plus 1 over 2 minus 1 over 3 plus 1 over 3 minus 1 over 4. Again, the 1/2s are gone, the 1/3 are gone. All of those internal fractions are gone, and we get 1 minus a 4th. So that's enough investigating for me to say, all right, I can come up with a rule now. I can say that Sn is going to equal, or in general, Sn is going to equal 1 minus 1 over n plus 1. So then the limit, I can do this. I can say that the limit, S equals the limit as n approaches infinity of Sn, or running out of space a little bit, limit as n approaches infinity of 1 minus 1 over n plus 1, which we're going to have 1 minus 0, or just 1. So ultimately, right, as we get further and further out with S3 or A3, A4, A5, etc., those fractions are getting smaller and smaller and smaller. The denominator is growing. That first fraction, the S1, is still just going to be, it's going to start with 1. It's really 1/2, but it's starting with 1. And then we're subtracting something approaching 0, something very, very small. So we're always going to end with 1. All right, so I'm going to stop us there. because I do want to talk about the new schedule just a little bit.